All right, so this is for assignment 3.5. Here we are. So let's get started. Number one, so this lesson has to do with related rates. Now, in order to do a related rate, obviously you've watched the lesson already. The lesson before was on implicit differentiation. Let me get that out of the way. And we used y prime in that case. And we understood y prime was dy by dx, but we just used y prime. But in this case, we're going to have an x prime as well in this case. And so for this situation, it matters what we're taking the derivative with respect to. So when it's related rates, it's with respect to time. So now y prime is not going to be dy by dx, but now y prime is going to be dy by dt. And x prime is going to be dx by dt. That means that whenever I take the derivative of either variable, you're going to need these hooks that are connected to it when we do it. And that's what we're going to practice right now. Now, the challenge will be when it becomes a story, being able to read the story, understand the story. There's going to be some geometry that we're going to need in the story, and we're going to go step by step through that when we get there. So let's start with number one again. So for number one, it says, here we go. You're given that dx by dt equals 3, that x equals 4, and that y equals x squared subtract 2x, and you're asked to find dy by dt. So in order to find dy by dt, I'm going to start here with y equals. I'm going to take the derivative. Now, if I take the derivative of y, that answer is 1. But it needs the hook because it's with respect to time. And the hook is dy by dt. If I take the derivative of x squared, it needs that hook. And that hook for x squared is 2x. And it needs that hook of dx by dt. And again, negative 2x also needs that hook. So the derivative of negative 2x is negative 2, but it needs the hook dx by dt. So every time you're taking the derivative now with respect to time, we need to be able to have that hook that's included into it. Okay, so next, when I multiply this, let's fill in some numbers. So I'm told that x is 4, that dx by dt is 3. So now I have numbers to plug in, and then I answer it. So 2 times 4 2 times 4 is 8. 8 times 3, 24. Take away 6. So this is equal to 18. Done. So that's the skill we're going to have. Now the real skill is going to be in being able to read the stories, but we need to start there. All right, number 2. In number 2, we have given that dx by dt equals 10, y equals 5, and you're given this equation, which is the equation of a circle, and you're asked to find dy by dt. So again, we're going to take the derivative here with respect to time, and that means every time you take the derivative, it needs a hook, dx by dt or dy by dt, knowing what variable it is. So x squared, the derivative is 2x, but it needs the hook, dx by dt. Y squared, that's 2y, but it needs the hook, dy by dt, and the derivative of any constant is 0. Now we substitute in. So we're told that x, we're not even given what x is. So we're given what y is, but not given what x is. So now what do we do? Well, I go back to the equation, realize I could solve to find a value that I don't know. So the equation is x squared plus y squared equals 169. So I know what y equals, and so I can substitute in and then solve for a value that I don't know. So 5 squared is 25. Subtract 25 to 169. I think it's 144. Take the square root, and the answer is 12. Now, the answer could be positive or negative, and we're not told which one it is. So when I substitute in here, I'm going to substitute in and understand that it could be positive or it could be negative 12 that I plug in here. I am told that dx by dt is 10. I said the y value is 5. And we're just going to solve that. Now, without being confused by understanding it's positive or negative, just multiply the numbers. So 20 times 12, that's 240. Now, the interesting part here is when I solve it, for positive, I would subtract. For negative, I would add. So in other words, when it goes to the other side of the equation, it's going to still stay positive or negative, because for one you would subtract and for the other you add, so those signs stay. Divide, and the rate when you divide could either be positive or negative 24, and you have your answer. All right, number 3. So in number 3, you're given the radius of a circle is increasing. So it's a little story, not too hard. The radius of a circle is increasing at a rate. So whenever you're told about a rate, then it's going to be a derivative that you're going to write down. So if the radius is increasing at a rate connected to time, we're going to let r be the radius. So that means the rate would be the derivative of the radius with respect to time. So when I look at the question, it says the rate is increasing. That word increasing matters because that means this number is positive 3. If it said the rate was decreasing, then you'd have to write the rate as negative 3. Okay. Next, it says at the instant the radius is 4 centimeters. So I'm already told what the radius is, which is 4. I'm told the rate is increasing at 3. And then it says A, find the rate of change of the area, and then the rate of change of the circumference. So in order to answer A, I need to know the formula for the area of a circle. That's pi r squared. Then, in order to find the rate of change of the area, that's a fancy way of saying the derivative of A with respect to time. I'm going to take the derivative of A, which is 1, but it needs the hook dA by dt. The derivative of this is just the power rule. Pi is a constant. So 2 times pi is 2 pi. Subtract 1 from the exponent. There you go. But because it's with respect to time, it needs the hook dr by dt at the end of that derivative. Now I substitute in what I know. So I know the radius is 4. I know the rate is positive 3. And now you have your answer. So that's 24 pi. Do we have units here? We do. So we have centimeters per second. So this rate is in centimeters per second. Now, because it's area, it's not going to be just centimeters, but centimeters squared per second, because it's the rate of the area. So exactly when the radius is 4 centimeters, the area is increasing at a rate of 24 pi centimeters squared per second. B. In part B, it says the circumference. So I need to start with the formula. What is the formula for circumference? Now, there's 2 of them, pi d or 2 pi r. We're going to use 2 pi r because we're given radius. So 2 pi r. Then, how do I find the rate the circumference is changing? We need to take the derivative with respect to time. So the derivative of c is 1, but with respect to time, you need the hook dc by dt. The derivative of 2 pi r, remember 2 pi is just a constant, so the derivative of 2 pi r is just 2 pi, but we need the hook dr by dt. Again, in the question, it already told me the radius is changing or increasing by a rate of 3. So if I put this together, I get 6 pi. And then what's the correct units for circumference? Well, for circumference, it's just centimeters. It's just distance around. It's just length. So it's not area. So it's just centimeters instead of centimeters squared. All right, number 4. Now we're going to get into the good stuff. So all of these are stories. We are going to annotate them together. We're going to not give up. We're going to work together The best is if you choose to pause and try it first on your own, and then after you've done that, to let me support you through it. So a large spherical balloon is inflated at a rate of 18 feet cubed per minute, and then when the radius is 2 feet, how fast is the radius changing? Read it first. Then, one sentence at a time, and can you take out the important information that you can get from here? So a large spherical balloon is inflated. So the first word I care about is spherical, and then inflated at a rate of 18 feet cubed per minute. When the radius is 2 feet, how fast is the radius changing? So first let's annotate what we have. So first of all, what geometric shape we have. We have a sphere. What do I know about the sphere? And we know how fast it's being inflated, and it gives me the units in feet cubed per minute. So if I know a rate, that means it's a derivative. So they give me the derivative for that. And 18 feet cubed per minute, that's the derivative of the volume. So they gave me the volume and how fast the volume is increasing with respect to time. And that volume increasing, because it's inflating, is 18. Now if it was deflating, it would be negative. All right, what else are we given? We're given the radius is 2. And the question is, how fast is the radius changing? So that's a rate. So that would be, I don't know this part. I want to know that how fast is the radius changing? What's the derivative of the radius with respect to time? Same question. Again, we're not given a formula to start with. So we need to know what we're talking about and what formula can we use for that. We're talking about a sphere and we're talking about volume. So I need a formula for volume of a sphere. So most of the time on the AP exam, in fact, you're going to be given these formulas. But you can go back a page to see the formulas on the sheet, right? They're in the lesson there, in a square. So the volume of a sphere is 4/3 pi r cubed. Interesting to me, maybe not to you, that when you take the derivative of the volume, it gives you the surface area. I find that intriguing because we've known some of these formulas, but didn't see the calculus connection to where they came from. All right, so we have a formula. Now what do? Is we take the derivative with respect to time. So the derivative of v is 1, but we need the hook dv by dt. The derivative of this is the power rule. 3 times 4/3 means the 3's divide out and give me 4 pi. Subtract 1 from the exponent, and I get 4 pi r squared. But it needs the hook. What's the hook? dr by dt. And then I can substitute in. So I'm not going to do it this way. So when we substitute in, you're given this, that the volume is changing at a rate of 18. So for dv by dt, plug in. The radius is 2. And what I'm asked to solve for is dr by dt. That's it. So all I need to do now is to isolate this, and I get my answer. So to isolate this, I'm just going to divide. This is 4 times 4. That's 16 pi. So I'm just going to divide by 16 pi. I have no desire to simplify this. There's no need to. It's the end of the question. 18 divided by 16 pi. Making sure I did it right, right? It's always a good thing. For sure. Number 4. Yep. And then after I do that, I need to make sure my units are, if there are any in the question, are respected. So radius is just the distance, a length. So it's just feet. And that's feet per minute. And then to write a good sentence. So we're going to practice writing a good sentence, not a long sentence, not a paragraph, just a good sentence that answers the question. So the question is, how fast is the radius changing? So let's start there. The radius is changing at a rate of 18 over 16 pi feet per minute when the radius is how big? 2 feet. So we answered the question and included the given information. That is a good sentence. So the radius is changing at a rate of 18 over 16 pi feet per minute when the radius is 2 feet. Perfect, not super long, not a paragraph, but it answers the question properly. Number 5. There it is. Another great story. Let's keep going. All edges of a cube are expanding at the rate of 2 inches per second. At the instant the edges are all 5 inches long, find the following. So let's annotate this together. So all edges of a cube, those are two big words, are expanding. Now the expanding is important because it tells me that it's a positive rate. And here it is, at a rate of this. Now if it used the word that's opposite of expanding, what would that word be? If it's shrinking, shrinking at that rate, you wouldn't see a negative number, but the word shrinking means that you must write that as a negative number. So you have to be a good reader to understand if it's positive or negative. And then the question is, at the instant, all edges are all 5 inches long, find the following. All right. So now let's write down what we know. So for number 5, first of all, it's a cube. Let's start there. Next, we know that the cube the edges of a cube are expanding at a rate. So again, when we're given a rate, what is that? It's the derivative with respect to time in terms of that. So we're going to use the letter E to be edge. And so the edges are increasing at what rate? 18 feet or inches per 18? Not 18. I was looking at the question above. 2 inches per second. And then what else do we know? Is that the edges are all 5 inches long. So the instant that the edge is 5 inches long, find what? So in part A, we're asked to find the surface area of the cube. So if I want to find the surface area, and I'm just going to call that dA by dt, if that's what I'm looking for in A, where do I start? And so it starts with understanding the geometric shape and what I'm looking for. So in other words, what is the surface area of a cube? So I'm just going to use the word A for surface area. Do you know the formula for it? Well, a cube is a square, and how many squares make up that cube? The area of each square, add them all up. If you play any board games and realize the dice or die, there are 6 sides, right? So 6 squares. Each square, once you know the edge or the side of the square, all you do is square it. So the area of one square is the edge squared, and then how many of those squares do you have to make up the whole cube? 6 of them. So 6 times E squared is the surface area of a cube. Then what we do is take the derivative with respect to time. So we'll do that. 2 times 6 is 12. And then again, make sure you remember the hooks with respect to time. Plug in the information you know. In this case, we know the edge is 5 and the rate is 2. So we plug that all in. 10 times 12 is 120. Make sure you know the units involved. So go back and make sure you know that. So in this case, it's inches squared, because it's area, per second. And now write a good sentence. So the question is, find the rate of change of the surface area. So the rate, the surface area is increasing, because it's a positive rate, is 120 inches squared per second when the edge length is 5 centimeters. So not a big, huge sentence, not a paragraph, just a simple sentence that answers a question that includes the given information. So the rate, the surface area is increasing, is 120 inches squared per second when the edge length is 5 centimeters. That's it. Part B. So part B asks for the rate of change of the volume of the cube. So for the volume of the cube, we need to know that formula. So if you take one edge and you cube it, that's where the word comes from, cubing, that gives you the volume. If I take the derivative with respect to time, I get 3e squared, and make sure that you include your hooks of derivatives in there. We're again going to plug in the edge is 5 and the rate is 2, and then just do the math there. So 25 times 375, double it, 150? Yep. And then make sure you know the units involved. So what is it? Volume. So the unit would be inches cubed, and this is a rate, so it's inches cubed per second. Good sentence. Ready? The rate, the volume is increasing is 150 inches cubed per second when the edge length is 5 centimeters. Great. All right, number 6. And remember, you can press pause, come back to it when you need to finish your assignment. The whole point is not copying what I'm doing, obviously, is having an opportunity to work with me, to get your work done with me, to learn from me, and to get to the point where you can actually try the work first, and then press play, and then see if you did it right. Point is moving on the curve, y equals root x. I'm just going to write down the things that I find important as I go through. So that the x-coordinate is changing at the rate of 3 centimeters per minute. So we're given a rate for the x-coordinate. So that rate for the x-coordinate I'm going to call dx by dt. The x is changing with respect to time. Is it increasing or decreasing? Is changing at the rate. Well, it's given us a positive one, and that's the only word, so we're just going to use that positive 3. When the y-coordinate is 25 centimeters, I'm going to write that down. Find the rate of change of the y-coordinate. So this is what I'm looking for as I break it down. So let's go one step at a time. So we already have an equation we're working with. So it's not a geometry question where we need to come up with a formula for volume or surface area or something like that. So we have something. So our goal is to take the derivative, substitute in what we know, and then find what we don't know. So to take the derivative here, I'm first going to write it calculus friendly. I'm going to take the derivative with respect to time. So we have 1/2 times 1 in front, subtract 1. So 1/2 take away 1, there it is. Make sure you have the hooks correct. We've been practicing this enough. So what am I looking for is dy by dt. So do I know the x-coordinate? And the answer is I'm not given it directly, am I? So the next question is, can I find that value to plug in? So I'm given the y value, but not the x. So I'm going to take that equation, and I'm going to plug in what I know. So I know that the y value is 25, and I'm looking for the x value. So to find this x value, using this equation, so I can then plug into here, I need to square both sides, and that's 625. All right, so now I have a value for x that I can plug in. So I'm going to plug that in, 625 to the exponent negative 1/2. And then dx by dt is 3. So I have our values that we're plugging in. Now I just simply have to simplify and units. So we have centimeters per minute. Just make sure that's included. So what do I have here? So the 1/2 means square root, but the negative exponent means reciprocal. So the square root of 625 back to here is 25. And it's the reciprocal. So it's 1 over 25. So if I put this all together, I get 3 over 50. What are the units? And it's centimeters per minute. And then write a good concluding statement that answers it. So the question is, find the rate of change. So I'm spelling okay. So when you use the words increasing or decreasing, it means you're using a good calculus word and you understand the meaning, the context of what you found. So that y-coordinate is increasing at a rate of 3/50 centimeters per minute when the x-coordinate is 625. Done. You could also say when the y value is 25. Both would be correct. Number 7. In number 7, let's read it. Now, it's a good thing that we have a picture here to help us too. This is what they call a real classic calculus question with related rates, which is a ladder slipping down a wall. And for an old timer like me, in terms of when I took calculus a few years ago, a lot of years ago, these are the questions that we would see. Eventually, that would be the introduction of related rates. You have a ladder slipping down the wall, and you have to find something. So let's do this classic calculus question together. So a 10-foot ladder is leaning against a house. So on the picture itself, I'm told this ladder is 10 feet long. Go right to it. The base of the ladder is pulled away from the house. So notice that B is being pulled away from the house at a rate of 1.5 feet per second. So what does that mean? How do I write that down? So because we're using A and B, this is a rate for B. So the rate for B is 1.5 and it's feet per second. So that's the rate that is being pulled away. And it says the instant the base of the ladder is 6 feet from the house. So that means the base in this case is 6 feet. Find the following. So find the rate at which the top of the ladder is moving. So that means I want to find dA by dt. Find the rate at which the area is changing. And then is this area from part B increasing or decreasing, and so on. And would your answers be the same at all times? And so we're going to answer each part of this. So let's come back here. So for number 7, I'm going to redraw just the picture of what I need, which is a right triangle. So here's my right triangle. What I know is the ladder is 10 feet. This is B, this is A. Now, for these related rate questions, it's essential that you understand what is a constant over the story and what is changing over the story. So it's essential. So why do I label 10 feet here, but these are A and B, even though I'm told B is 6? It's because A and B are changing over time. Their size is changing. They might be getting bigger. B is getting bigger. A is actually getting smaller, but the ladder stays the same size throughout the whole story. It's a constant. It doesn't change. So I can plug that in immediately. Now, because it's a right triangle, I know how these sides relate to each other, right? The Pythagorean Theorem, which is a squared plus b squared equals c squared, and I know c is 10. So I have this relationship already, that a squared plus b squared equals 100. What else do I know in the question? Well, it was told that the rate for B is 1.5. I'm told that B is equal to 6. And the first question is, find the rate at which the top of the ladder is moving. So that means the top of the ladder here, as it goes down, that rate would be dA by dt is what I'm looking for part A. So let's look at that right now. So we'll start with an equation that we have. A squared plus b squared equals 100. Take the derivative. So the derivative of a squared is 2a, but it needs a hook. The derivative of b squared is 2b, but it needs a hook. And the derivative of 100 is 0. Now, my goal is to find dA by dt. There's my goal. Do I know the value of A? No. Can I find the value of A? Yes. So if I see this equation, can I plug in the value for B and solve for A? Yes. So let's do that. So it's a squared plus 6 squared equals 100. And then we're going to solve that. So this is 36. So 100 take away 36 is 64. Take the square root of 64. Now the question is, should the answer be positive or negative? Because it's a real world situation, that distance here from the top of the ladder to the ground has to be a positive number. The rate, however, in fact it will be, could be positive or negative. In this case, the rate is negative, which tells me it is decreasing when I solve it. So I already recognize this rate is decreasing over time. A is getting smaller while B is getting bigger. So when I solve for it, it makes sense that the answer is going to be negative. Okay, so let's plug in. We know that A is 8. Get this here. I'm looking for dA by dt. I know that B is 6, and I know that dB by dt is 1.5. So we're plugging in the information that I know, and then I'm solving for what I don't know. So now just solve the equation. This is 16. Here, 12 times 1.5. Without a calculator, I would go 12 times 1, that's 12. 12 times 0.5, in other words, half of 12, that's 6, and then add them. That's like using the distributive rule in your head so that you can do the calculation without a calculator. So 12 plus 6, that answer is 18, and when you subtract it to the other side, it's going to be negative 18. Then, to get it by itself, the dA by dt, you divide. I don't need to simplify, but I need to know my units. So A represents a distance, a length. So in this case, it is feet per second. So what does that mean, that negative? It means that that distance is getting smaller over time. It's decreasing. So the rate at which, or let me write it differently. So let's write it this way. The top of the ladder is decreasing at a rate of 18 over 16 feet per second when the base is 6 feet out. So I want you to notice something, that I didn't mistakenly not put a negative in there. Instead, I used a great calculus word, which is decreasing. So the top of the ladder is decreasing at a rate of 18 over 16 feet per second when the base is 6 feet out. Now, if I write down the word decreasing and I put a negative in, then it would be wrong. It would be like two negatives making it a positive. So the word decreasing means it's negative, so we don't want to make the mistake where we write down the word decreasing and write it as a negative number. All right, that was only part A. Let's go to part B. Part B says find the rate at which the area is changing. So we need a formula for area. So the area is 1/2 the base times the height. So there's my formula for area of a triangle. I need to take the derivative of this. So the derivative of A is 1, but it needs a hook. Now I need to be careful. This is a product rule. So I need to make sure I do the product rule when I do this. So I'm going to say 1/2 A is the first and B is the second. So what is the product rule? It's the first times the derivative of the second. Now the derivative of B is 1, but needs the hook, plus the second times the derivative of the second, and again it needs that hook, dA by dt. So recognize the product rule when we do this. Substitute in. So we just said A was 8. dB by dt is 1.5. B is 6. And we just found dA by dt. So we might want to simplify it to put it in, but we can use our calculator here. I wouldn't say it's bad to use a calculator here. So substitute in. So that negative 18 over 16 is what we found, right, that we're using for this. So plug that all in and then simplify it. So if you did that correctly, you would get 21 over 8. Now the units matter. It's squared because it's area. So 21 over 8 feet squared per second. So put this and this in your calculator. You can write that. That's the answer as a fraction. The answer is a decimal. I don't know, 2 point something. Not quite 2.5. 2.5? No. So 21 divided by 8 will be a little bit more than 2.5. All right. So there's your answer. What's a good sentence? The area is increasing at a rate of 21 over 8 feet squared per second when the base is 6 feet out. So we're giving the answer and the condition of it at the same time. Part C is the area increasing or decreasing? would your answer be the same at all times? So the answer, quick answer to that one for C is it increasing or decreasing? We already answered that, right? It's increasing. Why? It is increasing. Why is it increasing? Because it's a classic AP type question. So we can answer it this way. Why is it increasing? Because the derivative is greater than 0. And then the next question is no, dA by dt could be positive or negative because it's a rate. So the area, the rate for the area could be positive or negative. So it could be the area is increasing, but there might be a time where that suddenly, in fact, there would be a time where the area is decreasing, where the base is so far out and it has just a little height that that area now is decreasing in value rather than increasing. So the first question is at that point, is the area increasing? The answer is yes. Second point, would that always be the case? The answer is no. Definitely the rate could be positive or negative. Done. All right, number 8. This video is going to go to number 10, just so you know, for your head. So again, you can take a break at any time, come back, press pause. The wonder of a video. A rectangle is formed whose length is twice the width. It is enlarged to a similar shape rectangle as the width changes at a rate of 4 inches per minute. When the width is 10 inches, how fast is the area of the rectangle changing? So first, read it. There seems to be a little jumbly stuff going on. So then we break it down, one sentence at a time. So I love that you could press pause and try to analyze it. Don't do the whole question, just analyze it. Can you tell me the shape? Can you tell me the information given? Break it down before we start doing anything else. So try it, press pause, and then come back. All right, I trust you. You press pause first. So let's see if you did it. So first of all, the shape's a rectangle. There it is. And it says the length is twice the width. So I'm just going to write that down. L equals 2W. It is enlarged to a similar shape rectangle as the width changes at the rate of 4 inches per minute. So dW by dt is 4 inches per minute. When the width is 10, how fast is the area changing? So, how good were you? Were you able to understand the shape, understand an equation that comes from that, a rate to do with width, what the width is, and that what are we looking for? So let's start. So, the area of a rectangle is length times width. I want to find dA by dt. So I'm going to use the product rule because that's length times width. The product rule is the first times the derivative of the second with respect to time. The second times the derivative of the first with respect to time. And we have the derivative with respect to time. Now, my goal is this, right? So my length in this case is, I don't know yet. But because W is 10 and length is twice the width, then I know the length must be 20 or 2 times 10. So then I can plug in values that, if I don't know, I can use this to find the values I don't know to plug into what I'm looking for. So the length is 20. The derivative of the width with respect to time, so the rate is 4. The width is 10. And are we given this part? We're not. So we need to find the rate of the length. So from this equation, that would be dL by dt. 2W would just be 2 with dW by dt, that hook. And then I could use that information to realize that, the rate for the length is 8 by taking the derivative and using the information that we have. I'll make sure that I'm on track here to understand that it is 8. All right, let's put it in. Then let's complete it. So this is 80 plus 80. Yes, 80 plus 80. So that answers 160. And what's your unit for area? That'd be squared. And that would be inches squared per minute. Done. Okay, so now let's write a good sentence. So the area rate is increasing. Oh, the area is, let's write it this way. The area, I know, scratchy. The area is increasing at a rate of 160 inches squared per minute when, what information we're given? When the width is 10 inches. Done. All right, for me, turn the page, number 9. Again, we're going to get to number 10, then a separate video for after 10. Number 9, here we go. So number 9, this is a little bit more involved story. So we'll take our time, we'll do it together. At halftime of a football game, 2 fans volunteer, are attached together with a bungee cord, and positioned on the sideline at the 50-yard line. One fan runs along the sideline, and the other runs on the 50-yard line, and one has a rate of 4, the other rate of 3. At what rate is the bungee cord being stretched when the sideline runner reaches the 30-yard line? Okay, so for this one, we need to have a little understanding of a football field. Let me give you that. I just drew a football field. These are called the end zones. If someone has the football and is able to run into there, they get what's called a touchdown. A football field is 100 yards long. In the middle of that is called the 50-yard line. That's in the middle. And then how it breaks down is it breaks down into 10-yard segments. But that actually doesn't even matter in terms of this, I don't think. Oh, when it reaches the 30-yard line, so it would matter. So here we have the middle of the field, which is 50. And then we count down by tens until we get to 0. So the next section would be called the 40-yard line. The next one would be called the 30. Then the 20. Then the 10. And then finally, it's not called 0. It would just be the end zone or the end line there. That would be like 0. So it counts down by 10. In this question, let's see if I have a highlighter. I'll use a different color anyways. Is this a highlighter? Let's see what we have here. All right. I'll just use a pencil. So in this question, they start together on the sideline here, and it could be either sideline here at the 50-yard line. And it says they're attached with a bungee cord. And one person's running along the sideline, and the other person is running along the 50-yard line. So there's your picture of the story. And they're attached with a bungee cord. So as they're running, this here, as I connect it, this here is the bungee cord that attaches the 2 people. So you have 2 people here, and that one is running, one is running. I'm going to call one A and one B. And so A is running this way, B is running this way, and then you have a bungee cord I'm going to call C. So what relationship do you see here in a right triangle that describes the relationship of all 3 sides? So if we take one leg and the other leg and square it, it's equal to the hypotenuse squared. So you can see the Pythagorean theorem. If I take the derivative with respect to time, so every time I take the derivative, it needs that hook for A, B, and C. I want you to recognize that there is no constant here. So A is changing, B is changing, and C is changing. All 3 are changing. There are no constants here. So as the bungee cord's stretching, it's getting larger and larger. So I can't plug in any values yet. But now I'm going to read carefully to see what do I know. So first of all, it says one fan runs along the sideline. So our sideline is A, and A is running at a rate of, my computer's going to lose energy in a second. So let me just plug this in. There it is. Okay, so anyways, what I was saying, A, what rate's A running? And A is running at 4 yards per second. That's my Y. It says B, the one that's running along the 50-yard line, that's our B, is running at a rate of 3 yards per second. And then it says, at what rate is the bungee cord being stretched out? So rate is a derivative. Our bungee cord is DC. And that's what I'm looking for. So let's break this down just a little bit. I need to know some values that I don't know. So first of all, I need to know A. I need to know B. And it'd be good to also know C. I'm not given any of them yet, so I have to think through this. So what other information am I given? So I'm given when the sideline runner reaches the 30-yard line. So when they reach the 30-yard line, how many yards has that person gone? So from 50 to 30, the distance covered is actually 20 yards. So already I know that part. How about for B? And what do I need to know? Well, in order to find for B, I need to know what time it took A to get there. So the rate is 4 yards per second. So for 20 yards, how many seconds have gone by, and what would you do? Well, if I went 20 divided by 4, I would get 5 seconds. So in 5 seconds, A covered 20 yards. Well, in the same amount of time, what did B cover in the same amount of time? So for B, the rate is 3 yards. So if I go 3 times 5, that's now B is covered 15 yards. So the rate that B is going is 3 yards per second. 3 times 5, we have it. And for C, well, for C, I just plug it back into the Pythagorean Theorem. So when we do that, that's going to be the square root of 20 squared plus 15 squared. So when I solve that, what do I get? I get 25. So I got 20, 15, and 25. Now I have all the values I need. So I'm going to plug in. So for A is 4, the derivative, A is 20, and the derivative is 4. For B, it's 15, and the rate for B is 3. For C, it's 25, and what I'm looking for is that, dC by dt. So I put in all the values that I have. So 8 times 20 is 160. 2 times 15 times 3, that's 90. And then 2 times 25, that's 50. So that's what I need to solve for. So 160 plus 90, 250. And then divide by 50 to get dC by dt by itself. So divide by 50, and I think you get 5. So the end sentence here, what rate? So the bungee cord is being stretched at a rate of 5 yards per second when the sideline runner reaches 30 yards. So we don't just write down the answer, we also write down the given information that goes with the answer, and now you wrote down a perfect equation that goes with it. All right, one more left, number 10. Another sports question, so I'm sorry for those that don't connect with that. I don't mean to isolate, but this one at least we have a picture. So a base runner who is running at a rate of 25 feet per second is halfway to first base. And so you can see a picture of a baseball diamond, and so here is what's called home plate. You hit the ball somewhere and you run to first before someone throws it to there and tries to get you out. Anyways, halfway there, so there the base runner is. It's good to know that anyways, find the rate of change from his distance from second base. So this distance here. So a couple things to know about a baseball diamond is that it's really a square. So there's a lot of geometry in baseball. One side of that square is 90 feet. So halfway here would mean this side would be 45 feet. And we're going to label this. Can you see here, because it's a square, that's a right triangle. So we have A, B, and C. And recognize that one of these sides is staying the same all the way. So this side right here, this 90 feet side, is constant. This distance, while the runner is running, because the runner is moving, two of these sides have a rate where it's not a constant. So I'm going to put this all together. I'm going to call this side C, that's the hypotenuse. I'll call this side A, and then this would be B, but it's just 90 and it stays that way. So let's put this together. So I know the Pythagorean theorem. In this situation, B is 90, and C is also changing. So any number that's fixed can go in before I take the derivative. That's a huge point. So I'm going to take the derivative now. So this would be 2a dA by dt. And recognize any constant will be 0. So that makes it much simpler. And then the derivative on the other side. Again, with respect to time. We found out that A is 45, that's halfway. The rate that they're going at, the baseball runner is running at a rate of 25 feet per second. So the rate for the runner is 25, plus 0 doesn't do anything. We said C is, we haven't found C yet, but we can. So for C, when A is 45, we have 45 squared, 90 squared, and then we could solve for C. So we just want to take the square root of that. You can use a calculator if you want. We don't want to use a decimal. We want the exact answer of that if it doesn't come out nicely. Well, in mine, they use a decimal, so that's fine. In my answer key, they had 100.623. So put that in your calculator. The best is, of course, is that you don't round until the end of the question. So the best would be to actually save it. So I'm going to show you that right now because it's a good example. So let's turn on a calculator. Press pause if you need to. So for my calculator, if I want to do that work, and I hope that you eventually will get this calculator from the library. I hope that works out. Control and x squared gets the square root sign. And again, in this case, it's 45 squared plus 90 squared. And then if I go control enter, it gives me the exact answer. I'm going to highlight over it. See how I push the cursor up? And then I want you to press control and C. Because control and C will copy it into the calculator, so it'll save it for you. So then, whenever I need that value, I can just plug that value in when I needed to get an exact answer. So I'm going to come back to this. So C is approximately 100.623, though we're not going to use that number. We're going to paste in the full number to get the most accurate answer we can. And this is what we're looking for. That distance to second base, what rate is that changing? So dc by dt in this case. So to get that answer, we're going to divide. And then use our calculator. So let's do that. Now notice the 2's divide, so I can just be done with that. So I'm going to use, press control and the divide sign. So control and the divide sign gives you a fraction. It's so much easier to have a fraction to type into often. So you have 45 times 25, move down, and you have paste. Now, how do I paste that number in? Is I go Control V. So Control V, paste it in, and then we're going to go Control Enter for the exact answer. And that's 11.180. There's one little mistake I made here. I'm going to show it to you in a second. So 11.180. Now you can round to 3 because it's the end of the question. Now, do anyone notice a mistake I made? So the mistake came right here. It's when I put in 25. Now 25 represents the rate, dA by dt. And what I need to be careful about the rate is whether that number, that side is increasing or decreasing over time. So if I look at my picture, as A is running, that baseball runner is running, do you see that A is shrinking as it gets closer to first base? It's getting smaller. So because the rate is decreasing, that means this number should be, and it doesn't have to tell you, you do need to know within the story, that this should have been negative 25. So this should actually have been a negative 25, so that when I put that in my calculator, that negative, this would have been a negative rate, meaning the distance from second base to the base runner is decreasing over time the closer it's getting to first base. So let's write a sentence for that. So I'm going to call it base runner. There's my sentence. So the base runner's rate to second base is decreasing at a rate of, remember, I'm not going to put two negatives in here, 11.180, and that is yards per, not yards, feet per second. When what? So we need the condition. So when the base runner is halfway to first base. So there it is, 1 through 10. I'm going to do another video for the second half of the assignment. So I apologize again for the sport references. There is a lot of connections with math and sports and geometry and sports. That's why it's used. But still, I can tell you the AP exam is very careful that they don't use stories like this. There are times where they do get in trouble, the AP exam, that they give stories where a certain person, maybe with a certain background, has an advantage. And that isn't fair. So they try to be equitable, and that hopefully there are people that recognize that question was not equitable because a certain person had the experience of that question that made it easier and someone else didn't. And that isn't fair that happens. Anyways, I got your back on that. Mr. G Math here, over and out. I'm proud of you that you're doing your work, and until next time.